um, understanding or knowing, about hackathon can really, help you broaden your view of, what computer science is about. Yes?
When you record, do you use a double screen?
Hmm?
When you record, do you
Uh-huh.
use a double screen?
No, I do not use a double screen. When I record, I use this tool. So last time, for whatever reason, I dragged the screen to a different place. So it recorded a place, where, it's not where, the main focus is.
Oh, that's what happened.
That's what happened. So this time I double checked to make sure that, it is actually recording the main portion of the screen. Yeah. Hand. I thought there was a hand.
Oh, sorry.
Oh, okay. So, okay, you weren't trying to get my attention. Okay, good. Okay, so getting back to floating point numbers and doubles, this is 5.2.2, which is kind of the opposite of what we did on last Thursday. So instead of having an exponent of 10 that is less than 0, we start off with an exponent of 10 that is more than 0, okay, greater than 0. So the objective is to decrease the exponent of 10 one by one until it is 0, okay? So now the question is, how can we do that? You have a number, a mantissa, times 10 to the power of some number that is greater than 0. And you want it to go to 0 eventually. So what do you need to do when you decrease the exponent of 10 by 1? What do you need to do to the mantissa so that you are representing the same value? Times 10, right? Okay. So that means, hey, it seems like it's a pretty easy thing to do, right? So if I have 123 times 10 to the power of 5, for instance, okay, I just have to keep multiplying 123 by 10, and each time I decrease the exponent of 10 by 1 until the exponent of 10 is 0. Then I'm done. Pretty easy. Well, the problem is, what if I give you an exponent of 10 that is like 45? Okay, think about this. 1.23 times 10 to the power of 45. Okay, so I'll just write it down so that we can actually see what I mean. Okay, so we are talking about 1.23 times 10 to the power of 45. So you go like, well, that's not too hard, okay? Because the program will give me 123 times 10 to the power of what this time? 43, because we shift the decimal point until it becomes a unsigned integer. So now you just go like, okay, we can keep doing this. It's 1230 times 10 to the power 42. It is 12300 times 10 to the power 41. It is 123000 times 10 to the power 40, and so on. Do you think you might run into a problem? And what problem would that be?
You would run out of the max range of the number that should be represented by 64.
Exactly, because the mantissa itself is represented by an unsigned 64-bit integer. Even though it has a huge range, because 2 to the power of 64 minus 1 is a pretty big number, but it is not infinite, okay? It has a boundary, okay? It has a limit. And that limit turns out to have, let's see whether we can guesstimate how many base 10 digits we are talking about, okay? So how do we estimate? If I want to find out how many base 10 digits is 2 to the power of 64, basically minus 1, okay? How many base 10 digits are we talking about? Do you guys know how to kind of estimate that? Okay, so we want to find out the number of base, I moved my click somewhere, of base 10 digits for 2 to the power of 64 minus 1. Okay, so let me see if you guys know the trick to do this. So the trick to do this is to say 2 to the power of 10, which is 1024, is pretty close to 10 to the power of 3, which is 1000. So let me write it out. 2 to the power of 10 turns out to be exactly 1024, which is kind of close to 10 to the power of 3, which we know as 1,000. Is that okay? So we use this as an estimation method. So how do we use this? Well, 2 to the power of 64, okay, forget about that minus 1 because it's really inconsequential in this estimate, okay? So this is basically 2 to the power of 4, okay? We will leave that thing by itself on the outside. And then on the inside, we have 2 to the power of 10, and that thing raised to the power of 6, okay? Do we have any questions about this part? 2 to the power of 64 is basically 2 to the power of 4, which takes care of this 4 here, and then times 2 to the power of 10, but that number raised to the power of 6. Is that okay? So I hope your exponent is still kind of up to speed at this point, okay? So what I do now is to say, okay, I'm going to re-estimate this, okay? So the tilde equal is just, approximately. So it's approximately 16, which is 2 to the power of 4, times, in this case, I would say 10 to the power of 3, which is 1,000, and that thing raised to the power of 6. So all I'm doing here is really substituting 2 to the power of 10 with 10 to the power of 3, which is a very quick way to do an estimate, okay? So if you look at this number here, how many digits are we talking about? So it's 16 times 10 to the power of 18, right? So there are 18 digits just for this part here, and then plus 2 more, okay? So we are talking about somewhere between 19 and 20 digits. Is that okay? So the largest number you can represent using an unsigned 64-bit number is, quote-unquote, somewhere between 19 and 20 digits, which means it cannot quite get to the largest number of 20 digits, but it's more than what you can represent using only 19 digits. Yes, go ahead. You can solve for x, but then you need a calculator. This way, you don't need a calculator. You're just eyeballing the number and just guesstimating. It's like, okay, how big of a number does TAC have to give me in order to force my program to have to deal with floating point numbers? Because if you keep multiplying by 10, you're going to exceed that number. Is that okay? So, well, if that is the problem, okay, so that means 1.23 times 10 to the power of 45 is not going to work. You cannot just keep multiplying the mantissa by 10, because 45 zeros, okay, is quite a bit more than 19 to 20 digits. Is that okay? So what do we do then? What do you think? You get to a point, okay, where your mantissa has already reached its limit, okay? If you multiply by 10 one more time, it's going to overflow. So what are you going to do? How do you make room for another multiplication by 10? Exactly. Okay, very good. So in the notes here, it talks about how to deal with that. So the first thing is we have to make sure that there's room to multiply by 10. How do we make sure that we do have room to multiply by 10? So what we do is we say, as long as m is not less than the largest integer value, which we already know because of the assignment from the previous week, divided by 10. So you take the largest value of a 64-bit unsigned integer, divided by 10, and you make sure that m, as long as m is not less than that number, you keep dividing it by 2 to make room for another division by 10. Is that making any sense? Now, but every time you divide the mantissa by 2, you have to adjust the exponent of 2 by 1. Does that make sense? Because the idea is we want to preserve the value being represented as much as we possibly can, but we can play with the mantissa, the exponent of 2, and the exponent of 10. Is that okay? Now, how many times do we have to go through this loop in order to make enough room to divide by 10 again? What do you think? It's kind of a tricky question, kind of like a math question. So let's say you maxed out and go like, okay, if I multiply m by 10 again, it's going to exceed the largest number in, as an unsigned 64-bit number, okay? So now the question is, how many times do you have to divide that number by 2 in order for that number to be small enough so that you can multiply that number by 10 again? Well, it's a tricky question because 10 itself is not really a power of 2. So most of the time, 3 division by 2 is going, but there will be occasions where you need 4 because 10 is between 8 and 16. Okay? So most of the time it's going to be close to 8, which means if you divide it by 2 3 times or so, you will have enough room. But occasionally, you just get one case where it's so close to the maximum number, you have to divide it by 4 times in order to give you enough room for another division by 10. Okay? So that means there's no way you can actually use a fixed number division to know how many times to divide m by 2 in order to have enough space for another division by 10. I keep talking about division by 2. How come we have a plus 1 here? What is it? What is it for? It's for rounding, okay? Because if we don't have this plus 1 as in the numerator, then the error of this division by 2 is always going to err on the smaller side. Because floor is truncation. We're always going to lose a little bit of a value. So by adding 1 and then divided by 2, I'm using a trick that I described much earlier in this module that basically says, to the beginning, and you say, well, do we still have a non-zero positive exponent of 10? If that is the case, do it again. So this entire thing is in a loop itself. But the first step is also a loop, because when you search as long as, that tells you it's a loop. Unless you think like me, then it becomes recursion. But we are not going to go there. Are we good so far? Okay. So the rest of this slide really just kind of talks about once we can get either step done, in other words, once we get the exponent of 10 to 0, okay, what else do we need to do? Well, the rest is really not too bad, okay? So the one thing we have to do is E10 is now 0, so it's gone, okay? We don't have a power of 10 anymore. M2, is basically just the mantissa itself, but the mantissa is not quote-unquote normalized, because at this point, the mantissa is a 64-bit number. It's a huge number, right? So to normalize it means we have to kind of shift that binary point until the mantissa becomes 1 point blah, 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 blah. Okay? But that's not too bad, okay? Because, what we can do is we can do this part here. But this is not what we want to do. Because if we do something like this, we're going to lose precision. So instead, what we're going to do is the bottom part. So we look at the bottom part here. And it says, as long as M2, which is the mantissa that we have at this point, is less than, if it is less than 2, which is what we need to fill up that mantissa, we want to double M2 and decrease the exponent of 2. It is greater than or equal to 2 to the power of 53, which means we got too many digits. Then we have to divide m by 2 and then increase the exponent of 2. So we are just basically adjusting things to make it fit the mantissa that we want. Are we still doing okay so far with this? Okay. All right. So when this is all done, we are now guaranteed a mantissa in base 2 that is between 2 to the power of 52 and 2 to the power of 53. Do you guys remember seeing something like that? A relation where a number has to be between 2 to the power of 52 and 2 to the power of 53? This is where it came from. Yep.
Just a point of clarification. Why is it that the mantissa has to be between those values? What is the benefit to making more exact? Let's say the value you want to represent
Right.
is 3.
Okay, so we want to write the code that works for all conversions. Okay, so also know that in the double, the actual mantissa that we are representing is 1 point and then followed by exactly 52 digits for the fractional part of the mantissa. Is that okay? So by doing this, we are basically making sure that we up with a number that has a 1 for bit 52, and then a whole bunch of digits for the rest of the digits. Now we're going to lose bit 52 because the 1 point is implied, but we'll keep the rest. So we are preparing for that particular by making the mantissa fit into this particular format. Is that okay? Okay. So once we end up with a mantissa like this, then what we need to do is basically do this mod operation. But the mod operation like this, basically we're just keeping track of the fractional part of the normalized mantissa. It's pretty easy to do because all we are really trying to do is to turn bit 52 to a 0. Okay? We keep all the 52 lower bits, bit 0 to bit 52, we keep. Bit 52, we turn it into a 0. We just get rid of it. Okay? But by doing that, which is an implicit shift operation, we also have to remember to add 52 to E2. Because what we have implicitly done, in this case, is we are shifting the binary point. So imagine that you have a huge number like this, and the implicit binary point is all the way to the right-hand side. So what we're doing with this step here is we are shifting the binary point 1, 2, 3, 4 all the way 52 times until it ends up here. But every time you shift the binary point to the left-hand side, you have to adjust the exponent to keep track so that the quantity or the value being represented is preserved. Is that okay? So once that part is done, we have to deal with E. So E2 is E minus 1023, which is the bias. So now that we know what E2 is, we have to add 1023 to E2. Whatever E ends up to be is an unsigned 11-bit number that we just have to shift into the right place in order to specify the exponent. Is that okay? And once that part is done, we just need the sign bit. The sign bit is the most significant bit. If the number or the value being represented is negative, then the sign bit is a 1. If the value being represented is not negative, then the sign bit is going to be a 0. So we just have to specify that one single bit as the last thing to do. And that will give us our double. Is that okay? Sounds pretty easy. But do you see how all of the topics, all the labs and your program, how they're all kind of connected? At least vaguely. Because sometimes we focus a lot on the pine needles and we don't get to see the branches or the tree. So sometimes we just have to kind of zoom out and go like, okay, how do these things all relate to each other? So do you guys all see a kind of connection between all of these things? More or less? Okay. So we do have a new lab tonight. Okay. I might as well just release the lab first. So the new lab is for positive exponent, which is based on section 5.2.2, whereas the assignment from the previous week is based on section 5.2.1. Okay. And it is not working. So is it me? Is it only this computer? Or is the website itself not working? Huh? Yeah, I still have a connection, so my connection is still good. Huh? I don't know. I don't know whether it's going to be the same situation at the lab. Nope, this is a Wi-Fi connection, but when you go to the... Well, it could be my computer too. Are you guys experiencing a similar problem, or is it just me? Okay. Okay, let me. Well, my cell phone is okay. My cell phone is still making a connection, and I want to make sure that. Okay, let me try this then. Okay, so give me a second here. I'm going to. Oh, it is disconnected. Okay, I'm going to reconnect. Okay, so let's try reload. Okay. So it could be just my Wi-Fi connection for whatever reason. Okay. Okay, so everything is back. Okay, the the lab is on. All right, so the lab is on. I'm going to release it and give you guys a week to work on it. Or we can do it the hackathon style, and I give you 24 hours. Let's do it the hackathon style. March 12th, 5:30 p.m. Yeah, March 12th. There we go. All right. So this one does give you a little bit more clue, to how to solve the problem. Okay, so it's actually a little bit better than the other one. All right. So we are technically done, not with the class, with doubles. Okay. So what we'll do now is to move on to additional topics. There are just a few more additional topics before we get to the actual assembly language programming. So this is about 1/2 through the semester. Remember at the very beginning, I told you guys that you will start to program in assembly in about at about 1/2 of the semester. So we're getting close to that. All right. So the new topic that we are getting into now. Sorry? Not graph theory. Now there is a connection between graph theory. Okay, but there is a connection between graph theory and what we are talking about. It has to do with compiler register optimization. Now, I don't think we want to get into that just yet, right? That's kind of like a graduate school topic. I know it's a graduate school topic because my roommate, when I was in graduate school, was doing that. All right. Oh, wait. Okay. A little too soon. Okay. Because I know you guys are going like, oh, do we really have to do this new topic thing? And the answer is yes, but I can make it a little bit softer instead of getting right into the technical stuff. Let's talk about the whole idea of what is a von Neumann architecture. Okay, now I don't speak German, so if I do not pronounce this last name correctly, you guys can help me pronounce it correctly, because I think, is it called von Neumann? Von Neumann? Huh? Von Neumann? Okay, so who's this guy? Why is he so famous? Okay, because I always want to look at people who actually make these inventions. So you're looking at an old dude, actually not much older than me, because he passed away when he was only 53, and I'm pretty close to that. Okay, so this guy is very interesting. Okay, he's very interesting because when you look at what he's good at, okay, when you look up Einstein, okay, who is Einstein? What kind of occupation? What is his specialty? Physics and mathematics. Okay, so two things. Okay, pretty good. So when you look at his field of contribution, it's a long list. Now, in history, there are many people who have a long list of interest and sometimes their expertise, but they may not make it all the way to Wikipedia because they make like only a little bit of contribution in each field. If you ask, okay, representation theory, I have no idea what that is, okay? If you ask a representation theorist, okay, about, okay, what is von Neumann's contribution, he will say, oh, he's a genius, he made a lot of contribution. If you ask a physicist, you will get the same answer. If you ask an economist, it will be the same answer. If you ask a computer scientist, it will be the same answer. He is an expert in every single field, okay? One of those really rare people, really, really rare people. If you look at his timeline, okay, you look at his birth and look at his death, he overlapped with Einstein, but not only in terms of the duration, like when they were both alive, they both taught at Princeton at the same time. So the story was Einstein was a very introverted person, so he prefers to work in a quiet environment where nobody is bothering him, okay? This guy, on the other hand, likes to listen to loud polka music when he's working, and they were in the same hallway. So you can kind of imagine the kind of conversation he might have with Einstein. The other thing that kind of tied those two scientists together was Einstein was the one who came up with the theory of E equals to mc squared. Okay? But he was the one who actually put it into the hydrogen bomb. So he put the theory into practice to build the hydrogen bomb. So they were kind of, so these two people, von Neumann and Einstein, actually, they had a lot of interactions. And many people, think that he passed away at age 53 because of the experiments, because he was exposed too much to radiation, and he died from cancer. So if this guy did not pass away when he was only 53, you can only imagine how much more contribution he can make to all kinds of fields. Which is kind of the same thing as, asking the question, what if Alan Turing, the father of modern day computer science, did not pass away when he was only in his 40s? What other things would he contribute to computer science if he did not pass away? So those are kind of interesting questions to kind of ponder upon. Okay, so now that you know who this guy is and that he's a super duper genius, now the question is, when people mention computer science, we only mention Steve Jobs and Bill Gates. So who is this guy? Right? I mean, before this class, how many people knew John von Neumann? Okay, so I could not surprise you. Darn it. Okay, so what was its contribution then? Yep.
He helped design the architecture of how computers are conventionally made and store information.
Very good. And before his time, how do we write programs and how do we change programs?
You had to change it physically through the way the computers were wired.
Exactly. So before von Neumann, okay, computers were hardwired. Okay? You don't just write a program. When you specify the behavior of a program, you are actually drawing physical wires, copper wires, from terminals to terminals. That is how you sequence operations. That is how you specify the pathway between the components of a computer. If you want to change your program, you open up the case of the computer, you unwire all those connections, and then you rewire the things that you want to wire up. So forget your over-the-air update of your Android or iOS systems, or just click a button to update all your apps. Okay, if it is not for him, okay, to update your apps would involve, guess what? Opening up your phone, go to the memory device or go to the processing device, use tiny little tools to disconnect a whole bunch, millions upon millions of wires, and then look up the diagram that these publisher would have sent you by mail, okay, and rewire everything up again, and hope that you don't make a single mistake in the process. Okay, so basically his contribution or the computers before him did not understand the concept of instructions in memory. The way you specify the behavior of a computer is physically wiring up the computer so that you can control, oh, this component, when it's done with this computation, it sends it to this component will do this kind of computation, and then after that it goes to this component, okay? It's all based on physical wiring. His contribution is to say, that is really difficult to update to a computer's program. It's difficult to change the behavior of a computer. Let's change the idea. Let us use memory, which was already used to remember to process data, but let's use the same memory to specify what the program is supposed to do, what the computer is supposed to do. That was his contribution. It does not sound like a big deal to us because we are so used to that idea already. Okay? But it's not just you, okay? Those of you who were in your 20s and 30s. Ask your parents. Okay? If you're in your 20s and 30s, your parents will be about my age, okay? And even people of my age would have floppy disks. Okay? If I want to update my program, on a computer, I would take a pile of floppy disks because one can only store 1.44 megabytes of data. But, it's pretty easy. You just have to keep loading, a floppy disk after floppy disk after floppy disk, and you can update your system. We didn't have to unwire stuff to update computers. You can even go further back in time, okay? If you ask your grandparents, okay, they might have used punch cards. Okay, you go like punch cards. I mean, that's pretty old-fashioned. That has to be, worse than stuff before Von Neumann. Nope, punch cards are still pretty good because nobody has to go to the back room to open up any computer to rewire anything. You just have to have an optical device to read the punch cards, and then that will update the program, and you can run the new program without having to open up the case of a computer. So that is its contribution. We don't understand the importance of its contribution because we are already so used to the result of his contribution already. Is that okay? It's kind of like, you guys thinking about, internal combustion engines, like, it's no big deal, I use it every single day. But remember, there was one time when there was no internal combustion engine. How do we get around? Horses? And what would be a problem with horses? Byproducts. Byproducts, which will dry up, turn into dust, and go everywhere. And we don't understand that because we are so far removed from those days. We are so used to internal combustion engine and all the modern stuff. So his contribution was great. It was really important. It's just that, we don't really experience, what computers were before his time, and we could not really quite appreciate his contributions. Okay? So that's kind of the introduction to this new topic, was to introduce the person first, who this person was and why he was important in this regard. So we are running out of time, so I'm not going to really get into the technical stuff of memory devices and whatnot. So you guys need to read ahead of me so that on Thursday, first thing, we can start with memory devices. Okay? I'm going to start my recorder or streamer now, and then we'll go to the lab.